Hello friends, welcome to Learner's Planet. Friends, this is our second session on theorems of on circles. In the last session, we discussed the basic concepts, terminologies on circles. In this session, we'll be taking some more concepts, more important points, aspects, theorems on circles. Okay, do revise the previous session before you come for this session, because whatever the theorems or important points I'm discussing over here, maybe in the previous session precisely, maybe they are useful in this session. Okay, so do revise the previous session before you come for this session. You should be ready with your copy and pen so you can note down the important concept as well. Okay, so let's begin the session. Now one more very important property: the tangent at any point of a circle and radius through the point are perpendicular to each other. Here we can say OP is the radius of the circle, the center of the circle is O, and OP is radius, and PQ is tangent. Tangent, that is the line that is touching the circle at any point, right? So OP and PQ, right? So OP will be perpendicular to PQ on this particular point, right? This is actually point of contact, right? The tangent PQ, the point of contact is P. If we draw a radius, if we draw the radius from point P, then the radius and the tangent will be perpendicular to each other. So precisely this angle is 90 degree, and that's really an important property. You'll be using this property many times when you'll be solving the problems. Okay, suppose a very simple thing I can ask over here: if the radius of this circle is 3, right, and this is suppose point P and this is point Q, and you are asked from point Q a tangent is drawn on the circle. Suppose this is O, QO, the tangent is drawn on the circle having length as 4. So find the distance between P and Q, or find the length PQ, right? If you know this concept that OPO will be perpendicular to OQ, then you can easily find out this length. That will be 5. These 3 will be Pythagorean triplets, right? But if you don't know, then you will be struggling. You will not be able to find out the length PQ. Okay, so you must be knowing this very important property. The length, the angle between radius and tangent, the common point is this, right? I'm sorry, they should have a common point, that is P, right? So OP and PQ, the OP will be perpendicular to PQ. PQ is tangent, OP is radius, radius is perpendicular to tangent. Okay. From an external point, over here we have an external point C. From an external point, if we draw two tangents on the circle, right, that is CA and CB, right, CA and CB, then both of them will have same length, right? From a common point, if we draw two tangents on a circle, then the length of both these tangents will be equal. So over here we are drawing a tangent CA and the other as CB, then CA will be equal to CB, right? Then the third thing that we have just discussed, OA, OB, here they are radius, so OA will be equal to OB, and the angle between the radius and the tangent is 90 degree, that we have just discussed, right? So this angle is 90 degree, this angle is 90 degree. Okay, and CA is equal to CB, and this length CO, it is common, right? So precisely triangle CAO is congruent to triangle CBO. Okay, so this angle will be equal to this angle because the two triangles are congruent to each other, and this angle will be equal to this angle. Okay, so once again, two important properties: CA will be equal to CB, that is the first one. OA is equal, angle OAC will be equal to angle OBC, both of them will be equal to 90 degree. Okay, and yes, the two triangles will be congruent to each other. Now next is, if two chords of a circle intersect internally or externally, then the products of the lengths of their segments are equal, right? Here the two chords, here it is AC and BD, they are intersecting internally, right? At this maybe at center, may not be at center. So the two chords are intersecting internally. O is not necessarily to be center. In that case, OB into OD is equal to OA into OC. See, OB, OD are segments of this chord BD, and OA, OC are segment of this chord AC. Okay, so OB into OD will be equal to OA into OC. Similarly, if they are intersecting externally like this, here we have chord RS and here we have chord PQ, right? If we extend them, PQ will be extended till O and RS will also be extended till O. So that precisely this chord being extended and this chord being extended, they are intersecting each other at point O. In that case, OQ into OP, I'm sorry, this is a printing mistake. OQ into OP will be equal to OS into OR. Okay, OQ, that is this segment, into OP is equal to OS into OR, right? Very simple problems can be asked, right? We have this, the length 3, this is 4, this is 2, then what will be the length of this part, right? So if we know this property, we know that this is 2 into X is equal to 3 into 4. So X will be 6. That means this portion will be 6. Right? So if you know this property, it will be very easy for you to solve this problem. Okay. So OA, the segment, the length of the segments will be equal. So don't be confused here. OQ into OP will be equal to OS into OR. Next important theorem, if a chord and a tangent intersect externally, then the product of the length of segments of the chord is equal to square of the length of tangent from the point of contact to the point of intersection. Precisely this AB is chord, but this complete line is a secant. That I have already explained you in the previous session what is the difference between a chord and a secant, right? Precisely if the chord is extended, it becomes secant of the circle, right? So PAB is a secant of the circle and PT is the tangent of the circle. T is the point of contact, right? So from the same point, if we draw a tangent and if we draw a secant, then the relationship will be PA into PB is equal to PT square. PA, that is this segment PA, PB, the total length is equal to PT square. Okay, so that is known as tangent secant theorem. Okay, so from point P we are drawing one tangent and one secant. So product of the segments PA and PB will be equal to PT square. Now we take the next property, we discuss the next property. We are having two circles which are touching each other externally. In that case, so this is the center of this circle, this is the center of this circle, this is the radius of this circle, this is the radius of this circle, right? So the distance between the circle, that is O1, O2, is nothing but the sum of radius R1 plus R2, right? If the two circles touch each other, the distance between their centers will be equal to sum of their radii, okay, R1 plus R2. And here we can have a common tangent also. So here it is a common tangent. Okay. Similarly, if two circles touch each other internally, right, the smaller circle is inside the bigger circle. Now what is happening? Just see carefully. The center of this circle is suppose O1, center of this bigger circle is suppose O2, right? This length is R1 and this complete length is R2, right? So the distance O1, O2 will be equal to, how do we find out the distance between O1 and O2? It is actually the complete length from this point to this point. It is nothing but the radius of the bigger circle, that is R2. From this, if we deduct this length, right, suppose this is point P. Okay, so O2P is R2, that is radius of the bigger circle. From that, if we deduct O1P, right, from this total length, if we deduct this length, we'll be getting O1, O2, right? So this length is nothing but the radius of the smaller circle. So that is R2 minus R1. So in case if the circle the circles touch each other internally, externally, then the distance between their centers will be sum of their radii, and in case when they touch internally, the distance between their centers will be difference between their radii, R2 minus R1. Here it is R1 plus R2, here it is R2 minus R1, where R2 is the radius of the bigger circle. Okay, here this is the common tangent, here this is the common tangent. I hope you are getting my point. Now we just go for a quick recap of all the formulae related to circle. Here circle, we have the circle, OP is radius of the circle, then radius is R, diameter of this circle, that is D, will be equal to double of radius, the length of the circumference, right? Circumference C is actually 2 pi r, where pi is 22 by 7, approximately it is equal to 3.14. Okay, basically pi is an irrational number. It's 3.141 something, a very big number is there. Since it is an irrational number, it cannot end. Approximately it is equal to 22 by 7. So according to the requirement of the question, you need to choose the value of pi, whether it will be 22 by 7 or 3.14. Okay, so length of the circumference will be 2 pi r. Okay, area of this circle is equal to pi r square. R is radius, pi r square, that is the area of the circle. Okay, similarly we can find out the length of major arc, minor arc, segments and all that, right? Suppose here this is the center of the circle, this is point P, this is point Q, right? So this is minor arc and this is major arc. Suppose this angle is theta. Okay, then if we have to find out the area of this sector OPQ, see OPQ is sector, right? So if we have to find out the area of OPQ, we'll consider this angle, that is theta over here, right? So the total area is pi r square. Out of these, see the total angle is 360 degree, of the center angle is 360 degree. Out of 360 degree, this is theta portion, right? So the area will be theta by 360 of pi r square, right? Pi r square is the total area. Out of that, see radius is the only variable part over here, right? Out of the total area, only this sector has theta angle, right, at the center. So out of 360, theta part will be the area, theta by 360 of pi r square will be area of this sector. Okay, so theta by 360 pi r square is area of sector OPQ, and if we deduct this from pi r square, right, we'll be getting the area of major sector, that is area of this portion. Okay, because this plus this, this plus this is nothing but the area of the circle. Okay, so pi r square is the area of total circle. This portion is area of minor sector, and if we deduct area of minor sector from the area of total circle, we'll be getting the area of major sector. Okay, so next is length of the arcs. Here this is minor arc and remaining is the major arc. So this arc, that is a part of circumference, right? And the differentiating figure will be this, the differentiating item will be this theta, this angle precisely, right? So total is the total length of the circumference is 2 pi r. Out of this, theta portion out of 360 will give you the length of this arc, right? So length of this arc PQ is theta by 360 of 2 pi r, and the length of the remaining portion is if we deduct this length from 2 pi r, we'll be able to get the length of the remaining arc. Okay, so area of major sector, area of minor sector, length of minor arc, length of major arc, you are clear now. Now this is diameter AB, this is the center of the circle, right? Diameter AB, AOB you can say. So this portion plus this portion. Okay, so this, the green line portion, that is actually semicircle. That is half of this entire circle, right? Now area of semicircle will be just half of the total circle, right? Area of semicircle will be just half of the area of the total circle, entire circle, right? But the perimeter will be different, right? Now perimeter of semicircle will be what? It will be arc length AB plus AB, right? Straight line AB. So it is arc length AB plus diameter of the circle, that is length AB. Okay, so arc length AB is nothing but half of 2 pi r, because this complete length is 2 pi r, so this is half of 2 pi r plus length AB, straight line length AB, that is nothing but the diameter of the circle. We can represent it as it as 2r. Okay, so precisely it is pi r plus 2r, that is the perimeter of semicircle. See, it depends upon the question whether you have to take the perimeter as arc AB plus length AB, straight line AB, straight AB, that is diameter, or you have to just consider this curved portion. It depends upon the question. Okay, if you are asked the total perimeter of this semicircle, then this will be the correct formula. If you are just asked the curved length, then it will be half of 2 pi r. Okay, so it depends upon the question. You should be conceptually clear about it, how we are deriving the perimeter or the curved length. Okay, now once again we are going to discuss very important points, aspects related to circle and triangle, right? Here I have shown two figures. This is a triangle and this is a circle. Now what is the speciality over here? This is the circle that is circumscribing this triangle. Circumscribing this triangle means all the 3 points of the triangles are there on the circumference of the circle, right? So we know it as circumcircle. Okay, when the circle circumscribe this triangle, then it is known as a circumcircle. That means all the 3 vertices of triangle are there on the circumference of circle, or we can say are there on circle. So this is circumcircle. This center, right, it is known as circumcenter. And the radius of this is known as circumradius. Okay, so this is a circumcircle, this is circumcenter, circumradius, and all the 3 terms I have told you. Now how do we draw this circle? Suppose I have this triangle, right? Not necessarily to be an equilateral or an isosceles triangle. It can be any triangle, maybe right angle, maybe scalene, maybe obtuse, any triangle, right? Here it seems to be obtuse angle triangle. So I'll just discuss the concept over here. It really doesn't matter which type of triangle is this. Now how do we draw the circumcircle? Now this is triangle ABC. Right, so if you use your compass and pencil, what you can do, you can find out the perpendicular bisector of BC. Okay, that will be something like this. Okay, this angle is 90 degree and this is the perpendicular bisector. Perpendicular as well as bisector. So this length is equal to this length. Similarly, you have to find out the perpendicular bisector of this. Similarly, this length. Okay. So this length is equal to this length is equal to this length is equal to this length. So the concurrence point of all the three perpendicular bisectors is circumcenter. Okay, the concurrence point of all the three perpendicular bisectors is circumcenter. Now if you put the point of compass over here and you take this as a radius O, A, suppose this is O, then a circle will be drawn like this. Okay, I'm not able to draw it neatly, but you can understand the concept, right? So OA will be equal to OB will be equal to OC, and OA, OB and OC, these are nothing but the radius of the circumscribing this circle, right? A radius of this circle. So precisely circumcenter is the concurrence point of all the three perpendicular bisectors of the triangle. So that's an important property, important definition. Circumcenter is the concurrence point of all the three perpendicular bisectors of the triangle. Okay. Or in other words, you can say from the center of this or from the circumcenter, the distance of vertices, right, that is OB, OC and OA will be same and they will be equal to radius of the circle. That's pretty simple. Okay. Now the interesting part over here, sometimes this circumcenter may be inside the triangle, sometimes it may be outside the triangle, sometimes it may be on a side of the triangle, right? If we take the case of a right angle triangle, I just draw the diagram very quickly over here. I have this right angle triangle. Okay, if I draw a circumscribing circle, precisely I mean a circle that is circumscribing this triangle. So this, you consider this to be over here. So this is a triangle, this is a right angle triangle, right? And you know the property that is angle in semicircle is 90 degrees. So if this angle is 90 degrees, that means this must be diameter. Okay. So in this case, when there is a right angle and we have a circle around it, in that case AB is diameter. In that case the hypotenuse will be equal to diameter of the circle, right? That means the radius will be half of hypotenuse. Okay, so if you know this property, you can solve this problem very easily. The question can be very simple. We have a triangle of when the length of the legs is 3 and 4. We have a right angle triangle with the length as 3 and 4. The length of the legs is perpendicular and base, right? Then what will be the length of the circum radius, right? What will be the measure of circum radius? Precisely we can the question can be asked, right? If you know this property, see, first of all you need to apply the Pythagorean theorem. If it is 3, it is 4, then it will be 5, right? The next property, the length of the hypotenuse is double of radius. Okay, so length of the hypotenuse is 5, so radius will be 2.5. So if you know this property, you can solve the problem very easily. Or precisely we can say the circumcenter will lie on hypotenuse, right? So because see, if AB is diameter, then obviously diameter passes through center of the circle. That means center of the circle lies on hypotenuse. So that's really an important property to be learned. Okay, center of circle will lie on hypotenuse of this triangle. Okay, and radius will be half of hypotenuse. Here the radius I mean is circumradius. Okay. Now here some important relationships I'm going to discuss. We have triangle ABC. The side opposite to A, I consider the length to be small a. Here it is B and here it is small c. Right? Now area of this triangle can be given as half A into C into sine of B. Okay, this angle, right? uh, this angle and the both the sides which are meeting over here. Okay, so half of AC into sine B, that is the area of this triangle. It can also be written as half of A into B into sine C. Similarly, it is equal to half of B into C into sine A. All of these are area of the triangle, so all of these will be equal. That means sine B into A into C is equal to sine C into A into B is equal to sine A into B into C. If we divide all of them by A, B, C, we will be getting an important relationship. That means sine B by B is equal to sine A by A is equal to sine C by C. So that is known as sine formula. Okay, or we can say A upon sine A is equal to B upon sine B is equal to C upon sine C. Okay, A upon sine A, B upon sine B, C upon sine C. Okay, so that's an important relationship. And the important thing, it is actually 2R. A upon sine A is equal to B upon sine B is equal to C upon sine C is equal to 2R, where R is circumradius. That is the radius of circumscribing triangle, right? I have shown the diagram over here. The radius of the circumscribing triangle, that means OA, OB, OC. OA, OB is equal to OC is equal to, I'm just treating it as capital R, right? That is circumradius of circumradius precisely. Now derivation is not important over here because that will be a tedious lengthy process. So you just learn the direct result. You must be knowing the sine formula, and I have already mentioned it over here, and derivation of the sine formula also I have told you. So sine formula, if we just take A upon sine A is equal to B upon sine A is equal to C upon sine A, that is equal to 2R. That is R over here is circumradius. One more relation over here is circumradius is equal to ABC upon 4 area of triangle. ABC, these are the lengths of the triangle, right? Area of the triangle, I'm just writing it as delta, or you can treat it as 4, maybe any other delta I just write. So circumradius will be equal to ABC by 4 area of triangle. ABC is ABC are lengths of the sides. Okay, so this is a very important relationship. You can use it in many problems. This sine formula, an important relationship. Area of the triangle, an important relationship. Okay, you can use any of the formula. If you know the length of A and C, and if you know this angle, then you can find out the area of the triangle. Similarly, if you know these two lengths, if you know this angle, then also you can find out the area. Okay, so it depends, whatever the data is given to you, according to that you need to use the formula. Okay, so this we discussed about circumcircle, circumradius, circumcenter. Next is encircle. When the circle is inside the triangle, right? All the 3 sides of the triangle, you can see they are working as tangent of the circle, right? So this is an encircle. The center is in center and the radius is in radius. Right? Now the next important question, how do we draw an incircle? I've already told you the radius, the angle between radius and the tangent will be 90 degree. Okay, so these angles will be 90 degree, and this is in radius. Now how do we draw an incircle? I have this triangle. These three are the angles of this triangle. If you draw the bisector of angle, right, that is the bisector of the three angles, then we'll be able to get the incenter. This is what incenter. Incenter is what? The concurrence point of angle bisectors. Concurrence point of angle bisectors. Okay, so this is incenter and this will be incircle, like this. Okay, so this is in radius, this is in center, and this is in circle. We assume the radius of this incircle is r. Now r is equal to area of triangle by S. Here S is semi perimeter of triangle. Okay, that is A plus B plus C by 2. Here A, B, C are sides, as we have already discussed in this triangle, right? The same triangle, triangle ABC, A, B, C are the lengths of the sides. Okay, then area of the triangle, if we divide it by semi perimeter, we'll be able to get in radius, that is radius of incircle. So the two relationships, r is equal to ABC by 4 area, and small r, that is in radius, is equal to area of triangle by semi perimeter. X radius, that is circum radius, is equal to ABC, that is product of the sides, by 4 area of the triangle. So these two relations are very important. So friends, we have discussed so many concepts, important points, terminologies, theorems on circles. I tried my level best to touch all the points. Maybe 1 or 2 points are left, so that we can take while we will be solving the problems. In problem solving sessions, you can just note down the points if anything you find important, okay, which have not been discussed in these basic sessions. Okay, so I'll see you in the next session once again. Bye bye.